All right, welcome here. Today's lesson is going to be online, and we're doing Notes 3. Now, if you don't have Notes 3 at home, where you can find it is on the Google Classroom, and you go to Chemistry Notes, okay, or Chemistry Material, I think I call it. And you'll see this Google Doc, and this is where you go. And this video is linked right here, but not yet because I'm making it. But the blank notes are right here, okay, right down there. And also you're also going to need this thing. So open this up. You're going to get a physical copy next class, but have this open in a tab. So I'm going to open it here. Just click on it and boom, there it is. Pops up. And so you'll be referring to this throughout this lesson today, okay? Naming compounds sheet. Okay, so we're here in these notes. You're watching the video and filling in the notes. So your job is to fill these in. And we will refer to this sheet and our periodic table as we go today. So let's get going. We are talking about chemical bonding. We have learned about ions, and this is ionic bonding. And so as you can guess by the name, because they name things with purpose, ionic bonding is the bonding between ions. And the goal of chemical bonding is simply this. The goal of chemical bonding is for bonds to be stable and balanced. Okay, and so what do we mean by stable and balanced? Well, we talked about stability, right? We talked about the fact that sodium, this atom right now, is not stable because it's got this extra electron out here, right? It doesn't have a full shell, so it wants to get rid of it. We talked about how it's going to lose it in order to become more stable, but then it becomes unbalanced. And it has a charge of, remember, it lost an electron, so it's got a charge of 1 plus now. It's got an extra proton. And we talked about how fluorine would like to gain an electron because it's 1 short to fill its shell. And if it did that, then it would have a charge of 1 minus. And so now they're stable, but they're not balanced because this has a charge, okay? And these charges are strong. Okay, and so we've got a charge of 1 plus and a charge of 1 minus. And what do we know about charges? We know that opposites attract. Okay, and so what we could imagine happening here is we can imagine that this electron, I want this to be purple, that this electron got transferred to this one. And look at that, it's just a perfect fit. And so sodium and fluorine would just be perfect for each other, right? Because it could give 1 electron over to fluorine, and we could imagine that these are they're a happy pair. Are they both happy as far as their outside shells? Yeah, because this one's gone, and it's got a full shell right here. 1, 2, 3, 4, 5, 6, 7, 8. And fluorine is happy because it has a full outside shell. 1, 2, 3, 4, 5, 6, 7, 8. They're both happy. And are they happy as far as their balance goes? Well, 1 plus, 1 minus, they're going to perfectly balance out. So this is pretty sweet. It's a good deal for both of them. And so this brings us to the zero-sum rule. And the zero-sum rule, I don't know what that circle is. Zero-sum rule is this, that the total of positive and negative charges in ionic bond must equal 0. The number of elements written is as a subscript. So I just want to highlight what subscript is. If you have like big letter A, okay, you could write X as a subscript, okay? And the reason it's a subscript is it's like a submarine, it sinks down. If I wrote, let's just put the letter M up here. This is not a subscript, this is a superscript. I don't think we use these much. You've seen these super heroes fly in the sky. I don't know, you use these in math as exponents. I don't know if we use them much in chemistry. So we're going to mostly focus on subscripts. This represents how many A we have, but A is not one. So we're going to talk about ionic bonds, how we determine how they're going to bond and how we name them. Okay. As we work on naming them, we will be thinking about how they form. Okay. We'll talk about this exception later. Here are the rules for writing chemical formulas. We start off by writing the symbols with charges as superscripts. Okay, so I start by thinking about, like, let's do an example right away with barium and oxygen. So we go to our periodic table and we look for barium. And barium is right here, okay, number 56. And so all we have to write out is Ba, and we also have to take note that it is here in column 2. So it has an ionic bond of 2. You can see here it's got 2 valence electrons. And so it's going to lose those 2 and it's going to have a positive 2 charge. So hopefully you saw this in your homework. So Ba2+. This is how I like to write it, as a superscript. Okay, this is just to help us get our final thing. And then we go back here and look for oxygen. Oxygen is right here. Okay, and oxygen has 6 in the outer shell, right? It is 2 away from being neon, from having a full shell, and so it's going to gain 2 electrons, so it has a charge of 2-. And just by doing this helps me to notice that if we had 1 barium and 1 oxygen, this would give 2 electrons over to oxygen, and they would both be happy, right? And so the way I write it is BaO, because 1 of each would be perfect. And these numbers helped us to determine that. Okay, because they're the same, we don't have to write anything. Technically, it'd be like 1, 1, but no one ever writes that. So don't write 1, 1. Okay, just write BaO. This is your final answer. I don't want to see ones. Any other number I need to see. Let's do the same thing with sodium. Sodium is Na. We don't care about the 11 anymore. We just care about this 1 over here. It has 1 valence electron, and it's in group 1. And so sodium is going to have a charge. It's going to lose 1 electron. So sodium Na is going to have a charge of 1+. Okay, so it's going to have 1 extra proton. Phosphorus, on the other hand, over here has 5 valence electrons. It's in column 5, group 5, and it's 1, 2, 3 away from being full. And so it's going to gain 3 electrons. So it's going to have a charge of 3-. Now this is weird, because if we add 1 sodium, it would look like this, Na. Let's do this Lewis dot diagram. Looks like this, right? Phosphorus, on the other hand, has a Lewis dot diagram like this. 1, 2, 3, 4, 5. All right. So we've seen this before. These are Lewis dot diagrams. Now, remember how ionic bonding is really just sharing of electrons? So we're giving away of electrons. So sodium could give away an electron here. But now this sodium ion is peachy. It is good. It's just like, I'm good. I'm stable. Right? And I'm attracted to phosphorus. But phosphorus is like, what? I got 2 more electrons that I need. And so what is phosphorus going to do? And so what phosphorus is going to do is going to find more sodium. And so what we're going to see is another sodium come along with another atom, and it's going to think, well, I see a pair I could take. And so what it's going to do is it's going to give away its electron, right? So this one's gone, and this one's going to be gone. It's going to go right there. And phosphorus is a little bit more happy, but not totally satisfied yet. Whereas this sodium ion is all peachy. It's all good. But we need 1 more, right? And so we're going to get 1 more sodium ion that's going to come along, and it is going to gift away its electron because it doesn't want it and phosphorus does. It's a mutualistic relationship. This sodium's happy, and now finally this phosphorus is happy. How do you know it's happy? Because it's got a full shell. It's got all its pairs filled. That's why I like to draw it the way I do. I want all the pairs filled. Any single electron on the outside is unhappy and waiting for a partner to come. And so what we see is for one phosphorus, right? One phosphorus atom needs 1, 2, 3 sodium ions. One phosphorus ion needs 3 sodium ions. And so where do we see these numbers here? We see the 1, but the 1 is with sodium and the 3 is with phosphorus. The 3 is how many charges it needs. The 1 is how many charges it needs. But phosphorus has 3 to give away in a sense, right? Well, it needs 3 and sodium has 1 to offer. And so what we're going to need to write is Na. We would need 3 of them, so we do that as superscripts. So what we're doing, or subscripts. So what we're doing is we're determining the subscripts that will produce a balanced charge. We would need 3 sodium ions, 1, 2, 3, for every 1 phosphorus. Remember, we don't write the 1 because the 1 is unnecessary. We check that the net charge is 0. Okay, this is step 3, is we check that the net charge is 0. And the way we do that is we think, okay, if we have 3 sodiums, this would be 3 1 plus charges. So that's a total of 3 plus there, right? Phosphorus, we've only got 1 phosphorus, but the 1 phosphorus is a 3 minus charge, okay, from phosphorus. And are they equal? Yes. They are going to cancel each other out. So we're good. And then we write the chemical formula. So this is the chemical formula. Okay, we've got 3. So we've done the first 2 examples. If you've got 2 elements, 1 metal and 1 non-metal, then we can create a ionic bond and figure out how they're going to bond. So we would need 3 times as much sodium as we have phosphorus, right? We have 3 times as many sodium as phosphorus. So let's keep going. Let's do these 2. Aluminum and arsenic. So we go here. Aluminum is right here. It's in a 3 column. It's got 3 valence electrons. It's going to lose 3. So it's Al3 plus. Arsenic is right here. It's in the 5 column. And so it is going to gain 3, right? So arsenic is As, right? And that's in the 3 minus. And now, how many do we need to balance? Well, 1 arsenic would take all 3 of aluminums that it's trying to get rid of, and so it'd just be a 1-to-1 ratio. Alas, that is what we get. Hey, that's correct. Yeah, awesome. It'd be 1-to-1 because they're both 3s, and then you never write the 1, but they're balanced. And so next we go to boron. Boron is also in that 3 column. So we got B has a 3 plus, and we're adding that to selenium, and selenium is right there. It's under sulfur and oxygen, and it's got 6. It is 1, 2 away from having a full shell, so it's going to gain 2. And so it's selenium, what is that again? Se, 2 minus. All right, and so how do these balance out? Now this is a weird one, so I'll try to draw this fast. We got a Se, it's got 1, 2, 3, 4, 5, 6. Okay, and we got a boron, and it has 1, 2, 3. And so it's going to give 1 away here, 1 away here, but it's still got an extra 1, so we need another selenium. So we get another selenium, 1, 2, and now it's finally got 1 to give away. Good. This selenium's good already. I don't know if I need that. Okay, that selenium's good. This boron's good, but this selenium's not good. So that means we need another boron. That's crazy. 1, 2, 3. And so this one's got 1 to give away. The selenium's good, but oh man, we need another selenium now, so this boron can be happy. And so 1, 2, 3, 4, 5, 6. Okay, this one can go here, and this one can go here. Now they're all happy. All right, so what we see again is we got 3 seleniums in order to satisfy 2 borons. Where do we see these numbers here? Well, we see 3 with boron and 2 with selenium. They're swapped, right? Isn't that exactly the problem that we had up here? We had 3 phosphoruses and 1 sodium, but we had to swap them, right? The numbers were kind of with the wrong element, and that's always how it's going to be. And so if they're the same, you don't write any number. That's what we did over here, right? It's 3 and 3, so then we swap them, but they're the same. 3 and 2, we can swap them and drop them. There's my tag, okay? If I had 2 borons and I had 3 seleniums like that, then they'd be balanced. Boom, that's our answer. We could double check. 3 seleniums of a 2 minus charge would give us a total of 6 minus. 2 borons with a 3 plus charge would give us a total of, well, 2 3 positives would be a 6 positive total. Wow, they'll balance each other out. So we know we're going to be good. Swap them, this one and that one, swap them and drop them down. So there's 2 borons, 3 seleniums. So the first step is always find these, okay? Find those charges, ionic charges. That's the last assignment we did. That's the tough stuff. Now, there's some, this is a bit tricky to make sure you got it right, but let's see if we can do it. Let's look. Our goal is to name these accurately, okay? And so let's find a name for, or here's how you name ionic compounds. Ionic compounds always happen between a metal and a non-metal. And we always name the metal first. All right? And so what do we name second? The non-metal. But what we do is we drop the last syllable of the element of the non-metal and we replace it with the sound ide, I-D-E, okay? And so some examples, if it's a metal, it's sodium and chlorine, it becomes sodium. We leave the metal alone, it's still sodium, but the non-metal becomes chloride, right? We drop it and make it an ide. Magnesium becomes phosphorus, becomes magnesium phosphide. Just this non-metal, we make it an ide. Aluminum oxygen, because not aluminum oxygen, but aluminum oxide. Okay. Okay. And here's where we're going to be using our sheet right away. The stock system is used only if the metal in the compound may have more than one charge. Okay. When does this happen? We're going to talk about it. This happens with these transition metals. Okay. These transition metals are here. Whoa. Okay. Yikes, I don't know what happened here. Anyways, these in the middle are transition metals on your sheet, and they can potentially have multiple ionic compounds, and we call them elements with multiple ions. Okay, so on your sheet, open up this sheet, and you'll see that you've got a list of 4 different elements. Okay, we've got copper, we've got iron, we've got chromium, and we got lead. These are the 4 that there are more, but I just want you to focus on these 4. Notice that it's possible for copper to have an ion that has 1+, but it's also possible for it to have an ion of 2+. And we don't know which one it is unless we write it out. So we're going to have to write copper always with brackets and describing which type of bond it is, what kind of ion it formed. Okay. There's iron 2 and iron 3. Notice this is a 2, which meaning 2+. This is a 3, meaning 3+. So whatever number you have here is the ionic charge of that particular ion. And so let's do some examples. The valence of the metal element is shown with a Roman numeral. All right. So here's what we do. Or here's some examples. They'll come up and I'll show you how to do that, okay? If we are given magnesium oxide, we've done something like this before. What we do is we go Mg. Now we think about Mg and it's right here. It's in the 2 column, and so it's 2 away. So it's a 2+. And oxygen is O, and it is also in the 2 column. And so we put it at 2-, so it's in 6, so it's 2 away. And so what do we get? They're the same number, so MgO is how we make the formula. So that's if we're given the name, then we can get the formula. Now, if we're given the formula to get the name, it's pretty simple. Al is aluminum, and Cl is chlorine, But do we write chlorine? No, we write chlor, and then we do ide. Okay, and there's your final answer. It's pretty simple. It's a lot easier to name it than it is to come up with the formula. CuCl2. Cu is copper. So this isn't so bad. But then we got to think, shoot, isn't copper one of these? It is. It could be copper 1 or copper 2. So we got to be careful. Now, how are we going to figure that out? Well, it's copper chlorine, and so that's going to be chloride. Same rule. The second one is always ide. It sounds so much smarter too. It's definitely worth it. But we need brackets. Copper what? It could either be copper 1 or copper 2. And we don't just choose randomly, though that would be fine. No, it wouldn't be fine. It's better than not guessing, but no, figure it out. Here's how we figure it out. There's 2 chlorines, okay? And 1 chlorine, well, chlorine's over here, and it is 1 away from having a full shell. So 1 chlorine would have the charge of 1, right? And so Cl has the charge of 1 minus, because each ion would gain 1 electron, but we have 2 of them. So we got a times 2. So the total charge would be 2 minus. And now how many coppers do we have? Well, we only have 1, right? 1 copper. And because there's no coefficient, or down on the bottom, there's no subscript. So there's only 1 copper. And it has to balance out the 2 minus that we got from the 2 chlorines, which means it has to have a charge of 2. And so we put the 2 in there. Okay, so we figure out what is the total charge of the second element, and we can apply that inside. So did we use copper 1 or copper 2? Well, definitely copper 2, because we needed a charge of 2 plus to balance out the 2 chlorines. All right, let's do the next one. Calcium chlorate. Calcium is right here. Calcium is in the second column, and so it has a charge of 2 minus. So do Ca 2 plus. I meant 2 plus, not 2 minus. Chlorate. Now this is weird. We wanted to do chlorine, right? But chlorine would be called chloride. So here's where I'm going to introduce the second part of the sheet. There are these things called polyatomic ions. Okay, what polyatomic ions are, they are ions, you might have heard of these, like ammonium, right? Or hydroxide, or carbonate, sulfate, phosphate. You might have heard of these bicarbonate, sodium bicarbonate. This is sodium bicarbonate is baking soda. And is that what we're making? Or are we doing calcium? Yeah, we're doing calcium chloride. Sorry, sodium bicarbonate is baking soda. So you've used that. These are compounds, okay, that have multiple atoms that also have an ionic charge. So they're still ready to make bonds. All right, so we call them polyatomic. Poly for more than one, like poly means multiple. Atoms, atomic, multiple atom ion. Ion means it still has a charge. An atom with multiple atoms that are bonded together that have a charge. That's a polyatomic ion. And so we are working with chlorate. That's what the question said. Notice how it says chlorate here, and then it's got ionic formula ClO3. So it's chlorine and 3 oxygens, and it's got a charge. Okay, so remember ClO3. ClO3 is chlorate, and it has a charge of 1 minus, right? Look over here, it's got a charge of 1 minus. ClO3 has a charge of 1 minus. Okay. We've got calcium that has a 2 plus charge, chlorate that has a 1 minus charge. We can swap them, drop them. So we would need 1 calcium to balance out, and I do a bracket, ClO3. This is chlorate, and we would need 2 chlorates. Make sure you've got brackets if you've got multiple of these polyatomic ions. Okay, so brackets, we've got 2 chlorates. Very good. That's it. So once you found their ionic charges, then you just swap them and drop them if you need to. Okay, we would need 2 of these because they each have a charge of 1, and so 2 of them would make a charge of 2 minus to balance out 1 of these, which has a 2 plus charge. All right, next one, K3PO4. Now this is weird because this PO4. I'm going to direct you back. Every time you see multiple ions at the back, okay, we've got our metal and we've got our non-metals, right? And it's always between the metal and non-metal. So the metal is easy. K is potassium. You can find that on your formula sheet. Sorry, not on your periodic table. We just list it. But what is PO4? You're tempted to write, don't write this, phosphorus oxygen or oxide or something? Question mark? No. And so we're not going to do that. What we're going to do is, get rid of that. What you're going to do is you're going to say, this stresses me out. I'm going to look at my cheat sheet. Okay? So call it a cheat sheet. I'm going to look for PO4. No. There it is. PO4. Oh, thank goodness it's on my formula sheet. It's called phosphate. So the name is phosphate. So I can go back to here and say, okay, it was potassium, and then it was PO4, and that's phosphate. Phosphate. Copy it exactly the way it's spelled, and that's it. That's all we have to do. Okay? Let's do it again. Ca, or pause the video and try it. Ca is calcium. NO3, come on, I hate these things. Actually, they're not that bad. If you look here, NO3 right here is nitrate. NO3 is nitrate. That's fantastic. Let's go over here, and all you have to write is nitrate. That's it. Well, what about all those numbers? What about that 2 there? We don't care about it when we're naming it. For naming, just write the names. PB, oh shoot. PB is also on our formula sheet. PB is lead, okay? So here we gotta be careful. These are the worst. It's either lead 2 or 4, so we gotta be careful. So let's just write out lead and put brackets, and we'll figure out what to put in there soon. PO4 is another stressful thing, but it's phosphate. PO4, we've seen before, it's phosphate. And so we don't write phosphorus oxygen, we write phosphate. But we gotta still figure out what to put in there. And how do we do that? We've got lead phosphate. Well, each phosphate has a charge of this, 3 minus. Every PO4 has a charge of 3 minus. Okay, so if each has a charge of 3 minus, how many are there? There's 2 of them, which means we got a total charge of 6 minus over here. Okay, so this also needs a 6 minus charge. Well, we got 3 of them, right? How do we get 6 minus on this side as well? Well, the way we do it is if we've got 3 something, 3 times what equals -6? We need it minus 2, right? 3 times -2 would be minus 6. So we need lead. Oh, sorry, this would be a 6. Yeah. There we go. We need it to be plus 6, right? Because we need this positive 6 to balance out the negative 6. That was my bad. And so we need a positive 2 charge for every one of these leads. Okay, and so we've got lead has an option of a positive 2 charge and a positive 4 charge. We're going to pick the positive 2 charge. Okay, so we put a 2 in here, and then we're done. Lead 2 phosphate. Very good. That's it. That's the notes for today. Tomorrow's class, we're going to be just working through stuff like this. Okay, you're going to get lots of practice time. So be ready for that. If you have questions, that's why we're working tomorrow's class. Today, your job was to follow along and do your best. Tomorrow, we're practicing, and I'll be available to help. If you're staying home, send emails, and I can do my best to help you. All right, have a great rest of your day.